Welcome back. This will be the solution to number 4 on our optimization worksheet. Number 4 says, find the area of the largest rectangle that can be plotted between the x-axis, y-axis, and this graph. All right, so the first thing that we need to do here is get a working visual of this graph, because this didn't come with it kind of already displayed. 8 minus x cubed, I can kind of piece together because I know what the graph of x cubed looks like. So y equals x cubed looks like that. This has a minus sign on it, so I'm going to interpret this as negative x cubed plus 8 and think about the plus 8 as the final transformation. So negative x cubed is just this flipped upside down. So that would look like that. So if I add 8 to this graph, it's just picking this up 8 units. So this squiggle point, instead of being at the origin, will be up at y equals 8. So same squiggle, but we're up at 8. It'll do this. So that's the visual that we see in the solutions provided here. So I'll draw it a little bit bigger and more clear. I don't need a ton of details. Like this graph is not perfect, but it has enough detail for us to get the sense of what they mean with the question. So if we have a rectangle plotted between the x and y axes and this graph, they're talking about a rectangle in this little window right here. That. So if we choose to put the corner of this rectangle way up here, we have a really tall, skinny rectangle. Or if we put the corner down here, we have a really wide, flat rectangle. So the question is, if you're changing that rectangle, what's the one with the maximum area? Yeah, okay. So I'm going to label the sides of this rectangle, because that seems like the right thing to do. This horizontal distance is the x value of this point. So I'm going to call this distance x and this distance y for a similar reason. And notice in this graph that this would be the point x comma y, whatever those side lengths are. Yeah. So in this one, the constraint is a little weird. It's a little trickier than the problems that came before it. So let's focus on our objective function first. They're saying find the area of the largest rectangle. So I want to maximize area. The area of this rectangle is x times y. That part at least is straightforward. And now the constraint is sneaky, right? They're not telling us you have, so many yards of fencing or so many square meters of material. But the purpose of the constraint is to turn this into a function of just one variable. So we need something that directly connects x and y to each other. So this formula right here, because this xy point lies on that curve, this is your constraint right here, y equals 8 minus x cubed. That's what we're going to plug in for y right here. Yeah, okay, so that's what we'll do. So we'll say area is now a function of just x. And I have x times, instead of y, 8 minus x cubed. So in this moment, it was really important that I had labeled my sides as x and y like that, so that x comma y, the point, does lie on the curve. This connection between x and y is true only for any point that's on this graph. It's not true for a point that's off of that graph. Yeah. All right, so from here, we just want to find the location of the maximum of this function, which always starts with critical numbers. So just like the previous problems, I'm going to clean up my area formula before I do the derivative step, just to make the derivative easier. So I'll distribute the x. I get 8x minus x to the 4th power. And I'll take the derivative. There are no domain restrictions here at all, so I just need to set it equal to 0. I'll add 4x cubed to both sides. Divide by 4. And then cube root. Because it's the cube root, I'm not plus or minus cube rooting. It's just the cube root. So my only critical number is the cube root of 2. You could put that in a calculator to get a decimal approximation, but because it's a decimal that doesn't end, you're actually, this is like the best way to write that number because it's the only exact way to write that number. Yeah. So we can see in this picture that X and Y should both be positive for this like scenario to make sense. So you could mentally put a restriction, like if we do the first derivative test, you could do that same restriction where X needs to be greater than 0, but you really don't need to. So if thinking about it too much kind of bothers you, because it's the only critical number, there's no need for us to cut the domain anywhere. We should be safe either way. All right, so this will be my A prime sign chart. I'm going to mark my critical number cube root of 2. And then we'll do test points on either side, hoping to confirm that this is the location of a maximum and not either a fakie point or a minimum. All right, so a number less than the cube root of 2, let's say 1. You could even put in 0 here. If we plug in 1 or 0 here, we get a positive output. Something bigger than the cube root of 2, let's say 100. We would have 8 minus a massive number, that would be negative. You could argue that this X value right here, you could figure out what that number is and say, well, that's the highest that you could plug in and plug in something tighter. But really, since this is the only critical number, any number over here represents that region. So we should be safe either way, even without cutting the number line. Yeah, so if A prime goes positive to negative, that means A went up and then down. So we really do have a maximum at this location. Let's go back and make sure we've answered the question as it was asked. Find the area of the largest rectangle. So this is the X value. We want to find the area. I do have the area function as a function of just X. I could use either one of these forms here. Or I could separately find the matching Y and then compute area as X times Y, but both those ways come out with the exact same number. So I'll just do the more direct path here. So if we plug in cube root of 2, I'll use this one here. So I'll have 8 times the cube root of 2 minus 4. Oops, sorry, I was looking at the derivative. So I'm plugging it in here. So I have 8 times cube root of 2 minus cube root of 2 to the 4th power. You can get it to a slightly nicer format if you plug it in here because you get to have the cube root and the cube cancel out. But either way, it's going to be kind of a messy number here. So since I don't have a calculator, I'll leave it in this format. Let me check to see if I have the number here. This is roughly 2.08. In case you're curious. Now, the units here are kind of tricky because no units were provided, right? We're just in the XY plane with no units. So if you could leave it just as it is and say, this is my area. Or you could say like cubic units, where units means, you know, whatever this is measured in, it's cubic those. But leaving it blank in a problem like this is okay because there were no units on X and Y to begin with.